space begins with a deception of scale. From the ground, the night sky appears crowded, almost overflowing. A black ceiling pricked by stars so numerous that the eye gives up counting them. The Milky Way can look like dust spilled across glass. A telescope makes the illusion stronger. It reveals more stars behind the first stars, more galaxies behind the first galaxies, pale spirals and red smudges and ancient clusters stacked into the distance. The universe seems lavish because light travels well through emptiness. What reaches us is the small, visible fraction of a much larger absence. To understand why space is so empty, we have to begin with what vision hides. The sky is full of signals, yet the places between the signals are immense. Between Earth and the Moon lies 250,000 miles of almost uninterrupted vacuum. Between the Sun and Neptune lie billions of miles where planets are rare islands. Between the stars of our own galaxy lie years of travel for light itself. Between galaxies lie distances so wide that even the brightest civilizations, if they existed there, would see their neighbors as ghosts delayed by time. The emptiness of space is therefore the main architecture of the cosmos. Matter is the exception, gathered into knots, grains, planets, stars, galaxies, and filaments. The larger pattern is separation. The universe was born dense, hot, and intimate, yet it expanded, cooled, and gave gravity the slow task of collecting what it could. Everything we call structure exists because emptiness was allowed to grow around it. The great question is simple and unsettling. Why did the universe become a place where almost everything is between things? In the beginning, space was not a stage waiting for matter to enter it. Space itself was part of the event. The early universe was hot enough that matter, radiation, and energy could not settle into the familiar forms we now recognize. There were no planets, no stars, no black horizons, no cold dust drifting through silence. There was a dense fire of particles and light, compressed beyond ordinary imagination, expanding everywhere at once. From that first expansion came the condition that still defines the universe today. Every region began to move away from every other region as space increased between them. This matters because emptiness is not simply a lack that appeared later. It is a consequence of expansion carried through cosmic history. As the universe grew, the same amount of matter occupied a larger and larger volume. Density fell, temperatures dropped. Particles slowed enough for atoms to form, and light was finally able to travel freely. The universe became transparent, which is another way of saying that emptiness had become large enough for light to cross it without being constantly scattered. The cosmic microwave background, the afterglow of that transition, still fills space as a faint record of the time when the universe first became open to vision. Yet expansion alone did not make the universe interesting. A perfectly smooth universe would have become a thin, featureless mist. The cosmos contained tiny variations in density, slight excesses and deficits inherited from its earliest state. These variations were small, almost absurdly small, but gravity is patient. Where matter was a little denser, gravity pulled in more matter. Where matter was thinner, expansion carried regions into greater isolation. Over hundreds of millions of years, these differences became the seeds of galaxies, clusters, and voids. Emptiness grew because the universe expanded faster than gravity could gather everything into one mass. Gravity works locally. It binds what is near enough, slows what is moving gently enough, and deepens what has already begun to clump. Expansion works across the whole fabric. It stretches distance on the largest scales, allowing islands of matter to become more isolated from one another. The universe we see today is the result of that long negotiation, gravity sewing knots into a widening cloth. There is a strange elegance in this. The same expansion that diluted matter also gave structure room to appear. Galaxies need space around them to be galaxies. Stars need distances between them to hold stable orbits and avoid constant collision. Planets need quiet neighborhoods where their atmospheres, oceans, and chemistry can survive. Emptiness is often imagined as hostile, yet without vast separation, the universe would be a violent blur, too crowded for the delicate arrangements that eventually lead to life. The human mind is trained by dense environments. Air presses against us. Water resists the hand. Stone feels solid because atoms inside it are locked into electromagnetic arrangements that push back. On Earth, matter seems abundant because we live on a planet, and a planet is a place where gravity has already done an extraordinary amount of gathering. We are born on one of the rare condensed islands, and then ask why the ocean around it is so empty. Even ordinary matter is only a small fraction of the universe's total content. Most of the cosmic budget is assigned to dark energy and dark matter, while familiar atomic matter, the kind that makes stars, planets, oceans, blood, and dust, accounts for only a narrow share. This fact changes the emotional scale of the question. Space is empty partly because the substance capable of shining, burning, cooling, and forming chemistry is limited. The visible universe is a thin, luminous writing on a much larger, invisible page. Dark matter deepens the paradox. It has gravity, so it helps gather galaxies and shape the cosmic web. Yet it does not shine, absorb, or scatter light in the familiar way. It forms halos and scaffolds, lending structure without becoming visible structure. Around galaxies, dark matter may dominate mass, while the stars occupy only the brightest inner expression of a larger gravitational form. Much of what holds galaxies together remains unseen, and much of what is seen occupies only a small part of the whole. Ordinary atoms are rarer still when spread across cosmic volumes. Inside stars, matter is dense enough for nuclear fusion. Inside planets, it is dense enough for geology. Inside nebulae, it may be rich enough to glow, collapse, or form new stars. Across the spaces between those objects, density collapses to numbers that feel almost like abstraction. A cubic meter of interstellar space may contain only a handful, hundreds, or thousands of particles depending on the region. By earthly standards, even a rich nebula is an almost perfect vacuum. This is one of the hardest truths to picture. The universe contains enormous amounts of matter in total, yet its average density is extremely low because the volume is so vast. A galaxy may hold hundreds of billions of stars and still remain mostly vacant. A galaxy cluster may contain thousands of galaxies and still be dominated by dark gaps, thin gas, and long distances. On large scales, abundance and emptiness coexist. The cosmos can be materially rich in total and sparse in every local stretch. The reason is geometric. Volume grows brutally with scale. A room can feel full with a few people. A city needs millions. A planetary system can contain a star, planets, moons, comets, dust, and still leave almost every cubic kilometer empty. A galaxy can contain stars in numbers beyond counting, yet spread them through a disk 100,000 light-years wide. The universe does not need to remove matter to become empty. It only needs to give matter enough room. The solar system is often drawn as a tidy sequence. Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, each planet placed like a bead on a string. Such images are useful and deeply misleading. They compress distance until the system becomes readable. In reality, the planets are tiny bodies separated by volume so wide that any accurate drawing would become almost blank. The Sun would be a small sphere, Earth a speck, and the distance between them would consume the page. Earth feels large because it holds us. Against the solar system, it is a small stone in a vast gravitational field. The Moon, our closest major companion, is far enough away that all the other planets of the solar system could fit between Earth and the lunar orbit in a rough line. Beyond the Moon, the inner planets circle in wide lanes. Mars, at its closest, still lies millions of kilometers away. Jupiter, huge enough to swallow Earth more than 1,000 times by volume, moves in an orbit separated from us by a gulf that spacecraft cross only with careful planning and months of travel. Between these worlds there is matter, though almost none by earthly standards. There is solar wind, a stream of charged particles from the sun. There is dust, shed by comets and collisions. There are fragments, asteroids, meteoroids, icy bodies, radiation, magnetic fields, and the thin breath of particles that fills interplanetary space. Yet the total density remains astonishingly low. A spacecraft crossing these regions does not push through a medium. It falls along calculated paths through a vacuum so clean that motion can continue for years with tiny corrections. This emptiness is why planets survive as distinct worlds. If the solar system were filled with thick gas, or with dense clouds of debris, or with swarms of large objects at every radius, stable orbits would be constantly disturbed. Collisions would be routine, atmospheres would erode differently, worlds would be ground down, scattered, or swallowed. The quiet between planets is part of their preservation. Earth has lasted for billions of years because it moves through a neighborhood that is mostly clear. The early solar system was far less empty. It began as a disk of gas and dust around the young sun. Within that disk, grains collided, stuck, grew, shattered, and gathered again. Planetesimals became planetary embryos. Some merged into planets. Others were thrown outward, driven inward, or left as remnants in belts and clouds. The emptiness we see now is the aftermath of a violent cleaning. The planets are survivors of a formation process that consumed, ejected, or rearranged most of the original material. So, our own planetary system teaches the larger cosmic rule. Structure forms by removing alternatives. A planet is what remains after countless smaller pieces have been gathered or cleared. An orbit becomes stable after chaos has spent itself. The space between worlds is the memory of construction. It looks vacant because gravity has already sorted much of the debris into a few dominant bodies and left the rest as trace material faint enough that sunlight rarely finds it. If the planets seem lonely, the stars are lonelier still. The Sun's nearest stellar neighbors belong to the Alpha Centauri system, more than 4 light-years away. Light from them spends years crossing what appears in telescopes as a modest local distance. A modern spacecraft moving at the speeds we have achieved would require tens of thousands of years to reach that neighborhood. In human terms, the nearest stars are almost inaccessible. In galactic terms, they are close. The average distance between stars in the Milky Way is often described in the range of several light-years. That number depends heavily on region. Near the galactic center, stars crowd more closely. In globular clusters, the stellar density can become far higher than in our local neighborhood. In the outer disk and halo, stars thin out into greater isolation. Even so, the overwhelming pattern remains separation. Stars are enormous compared with planets, yet minuscule compared with the distances between them. This comes from how stars form. They are born inside cold molecular clouds, regions where gas becomes dense enough for gravity to overcome pressure, turbulence, magnetic fields, and heat. A cloud does not collapse into one perfect object. It fragments. Different pockets become denser, collapse further, and ignite as stars. The newborn stars may begin in clusters, surrounded by gas and siblings. Over time, radiation, stellar winds, gravity, and galactic motion disperse many of those clusters, sending stars into wider orbits around the galaxy. A star is therefore a concentrated result of a much larger cloud. Most of the original volume never becomes stellar material. Some gas is blown away by massive young stars. Some remains too warm or turbulent. Some becomes planets, disks, or dust. Star formation is inefficient compared with the total volume involved, and the stars that do form are then spread through galactic space. Their brilliance makes them seem dominant. Their actual filling factor is tiny. The distance between stars also protects planetary systems. A close stellar encounter can disturb comets, alter orbits, and destabilize planets. In our region of the Milky Way, such encounters are rare enough for planetary systems to endure across immense spans of time. The Sun has moved around the galaxy many times since its birth, passing through changing stellar neighborhoods, yet its planets remain arranged in long-term order. The emptiness between stars gives solar systems a form of privacy. From a cosmic perspective, stars are like lamps placed far apart across a continent-sized night. Each lamp lights its own immediate surroundings, warms its own small family of worlds, and then fades into black before the next lamp begins. The Milky Way is bright when seen from outside because billions of stars overlap in projection. Inside it, from one star to another, The galaxy is mostly dark road. The word vacuum can mislead the imagination. It suggests perfect absence, a clean nothing, a region empty of every particle and every field. Real space is stranger. Even the most rarefied cosmic regions contain radiation, particles, magnetic fields, neutrinos, gravitational waves, and quantum fields. The vacuum of space is thin enough to humble every earthly comparison, yet active enough to carry the history of the universe. Interplanetary space contains the solar wind, a continuous flow of charged particles moving outward from the sun. It also contains the interplanetary magnetic field, dust grains, cosmic rays, and photons from the sun and from distant stars. Interstellar space contains gas and dust between stars, with density varying enormously from hot diffuse regions to cold molecular clouds. Intergalactic space contains even thinner gas, some of it heated to extreme temperatures inside galaxy clusters. The universe is empty in the sense of density, not in the sense of absolute vacancy. This thin material matters. Interstellar gas becomes the reservoir for future stars. Dust grains shield molecules, cool clouds, and provide surfaces where chemistry can occur. Magnetic fields influence how gas collapses. Cosmic rays ionize atoms and alter chemistry in dark regions where starlight barely penetrates. The sparse medium between stars is part of the galaxy's metabolism. It receives matter from dying stars, mixes it over time, and returns some of it into new stellar generations. The emptiness also permits motion at cosmic speeds. Photons cross immense distances because the universe is transparent across many wavelengths. Neutrinos travel through planets and stars with little interaction. Cosmic rays can cross interstellar space before being deflected by magnetic fields. Gravity reaches across the void, binding stars into galaxies and galaxies into clusters. The thinness of space allows influence to travel far, even when matter itself is scarce. A dense universe would hide itself from itself. Light would be scattered, absorbed, or trapped. Distant galaxies would vanish behind local fog. The cosmic microwave background would never reach our instruments as a clean relic. Astronomy depends on emptiness. We can see deep time because space is transparent enough to preserve ancient light. The vacuum is the archive through which the universe sends us its memory. This gives emptiness a second role. It separates objects, and it connects them. It keeps stars apart, while allowing their light to cross the gulf. It isolates galaxies, while allowing gravity to shape their motions. It preserves silence while carrying signals. The great voids are quiet, yet they are not meaningless. They are the medium through which the cosmos becomes observable. A galaxy is one of the universe's grand concentrations. Stars, gas, dust, stellar remnants, dark matter, planets, and magnetic fields bound into a rotating system. The Milky Way may contain hundreds of billions of stars, and from a dark place on Earth it can appear like a river of pale fire. Yet if we could shrink the galaxy to a scale the mind could hold, the stars would become tiny points separated by vast intervals. The glow of the Milky Way is collective, built from distance and number rather than actual crowding. Galaxies also possess invisible breadth. The visible disk is only part of the system. Around it lies a halo of old stars, globular clusters, hot gas, and dark matter extending far beyond the bright spiral arms. The luminous galaxy is the visible center of a larger gravitational territory. Even here, most volume is empty. A halo can stretch for hundreds of thousands of light years while containing only sparse matter compared with the condensed brilliance of the disk. Between galaxies, the distances grow severe. The Andromeda Galaxy, our large neighbor, lies about 2.5 million light-years away. It is visible to the naked eye under dark skies, yet its light began traveling toward us before modern humans existed. The local group contains the Milky Way, Andromeda, Triangulum, and many dwarf galaxies, all bound together by gravity. Still, the spaces among them are immense, filled with thin gas, dark matter, radiation, and time. Galaxy collisions reveal another side of emptiness. When galaxies merge, their stars almost never collide directly. The distances between stars are too large compared with stellar sizes. What interacts strongly are the gas clouds, the dark matter halos, and the gravitational fields. Tides stretch spiral arms. Gas is compressed into new star formation. Black holes may eventually spiral together. The galaxies can pass through one another in a slow transformation because the stars themselves occupy so little of the available volume. This is one of the most powerful demonstrations of cosmic emptiness. Two galaxies, each containing billions of stars, can overlap without turning into a storm of stellar impacts. Their shapes are torn by gravity, their gas ignites, their histories are rewritten, yet the stars travel through the encounter like sparks moving through a cathedral. The scale mismatch is almost unbearable. Enormous systems, rich with light, still mostly open space. Galaxies are therefore not solid cities of stars. They are gravitational climates, immense regions where matter has gathered enough to shine, rotate, and evolve. Their beauty comes from the fact that light fills the eye more easily than matter fills volume. A spiral galaxy looks complete from afar because its stars trace a pattern. Inside that pattern, space remains the dominant substance. Beyond individual galaxies lies the large-scale structure of the universe. Matter is arranged in a cosmic web, clusters and superclusters linked by filaments, with enormous voids between them. This pattern arose from the early density variations amplified by gravity. Dark matter gathered first into a vast invisible scaffold, and ordinary matter followed, cooling into galaxies where conditions allowed. The result is a universe that resembles foam, with luminous threads surrounding dark cavities. The voids are among the largest structures in existence. They can span tens or hundreds of millions of light years, containing far fewer galaxies than the cosmic average. They are not perfectly empty, yet they are profoundly underdense. A galaxy inside such a region would see a night sky with fewer bright external companions. Its astronomers might have taken longer to discover the large-scale richness of the universe. The cosmic web teaches that emptiness is not random. It has shape. These voids grew because gravity drained matter toward denser regions. Over time, the slightly emptier regions became emptier still, while dense regions became more crowded. Expansion helped amplify the separation. Matter moved into walls, sheets, and filaments, leaving cavities behind. The web is the fossil of countless gravitational choices made over billions of years. Every filament is a place where matter won a local contest. Every void is a place where matter gradually lost density to its surroundings. There is a philosophical weight in this structure. The universe is not a uniform field of scattered lights. It is a hierarchy of absences and concentrations. Planets gather around stars. Stars gather into galaxies. Galaxies gather into clusters. Clusters gather along filaments. Between each level lies a larger emptiness. The same pattern repeats with changing scale. Matter assembles into islands, and the islands reveal the sea around them. Modern surveys map this web with increasing precision. Millions of galaxies become coordinates in a three-dimensional history of expansion, gravity, and dark energy. The maps look alive, like nerves or roots, yet they are built from ancient light. They show that emptiness is measurable. Voids have sizes, boundaries, growth histories, and relationships to the expansion of the universe. They are not blank areas in our knowledge. They are part of the knowledge. The cosmic web also suggests why emptiness is inseparable from time. The universe did not arrange itself into filaments and voids instantly. It took billions of years for gravity to sharpen the pattern. When we look far away, we see earlier stages of that structure. We see galaxies younger, clusters less settled, voids still evolving. Space is empty because the universe has been expanding and sorting itself for almost its entire life. A natural question follows. If gravity attracts matter, why has it not pulled everything together? Why does the universe remain sparse after billions of years? The answer begins with scale. Gravity is powerful over time, but it must compete with expansion, motion, radiation pressure, heat, angular momentum, and the initial conditions of the universe. It can gather matter where matter is already close enough and slow enough. It cannot easily reverse the expansion of every region across cosmic distances. Bound systems resist the expansion of the universe. The solar system is bound by the sun's gravity. The Milky Way is bound by its mass and dark matter halo. The local group is bound strongly enough that the Milky Way and Andromeda are moving toward a future merger. On still larger scales, expansion dominates. Distant galaxy clusters are carried away from us as space grows between them. Gravity builds local structure while the largest distances continue to widen. Motion also matters. Matter in the early universe did not simply sit waiting to fall inward. It carried velocities, heat, pressure, and quantum inheritances. Gas resists collapse when it is warm. Radiation pushes. Magnetic fields complicate flows. Angular momentum prevents everything from falling straight into the center. A collapsing cloud often forms a disk, fragments, and redistributes material. Gravity gathers, yet it rarely produces simple closure. It creates systems with orbits, halos, jets, disks, and leftovers. There is also a limit to how efficiently matter can cool. To collapse into dense structures, gas often needs to lose energy. Cooling depends on atoms, molecules, dust, radiation, metallicity, density, and environment. Some gas remains too hot and diffuse to form stars. In galaxy clusters, vast reservoirs of gas shine in X-rays at temperatures of millions of degrees, spread across enormous volumes. They contain matter, but not in the condensed form that would erase emptiness. Dark energy adds another layer. On the largest scales, the expansion of the universe is accelerating. This acceleration increases the isolation of distant structures over time. Galaxies outside our gravitational neighborhood will eventually slip beyond practical reach, their light stretched and dimmed by expansion. The future universe may become more empty to any observer inside a bound galaxy group, not because matter disappears, but because the visible horizon changes and distant regions recede. Gravity, then, is not a universal janitor sweeping all matter into piles. It is a sculptor working under constraints. It deepens local wells, organizes galaxies, and forms stars from the right clouds under the right conditions. Across the grandest scales, expansion sets the background rhythm. Emptiness survives because the universe is too large, too dynamic, and too rapidly widening for gravity to gather every atom into light. The emptiness of space has an echo inside matter itself. A solid object feels continuous because electromagnetic forces resist compression and because our senses are tuned to surfaces. At the atomic scale, solidity becomes a pattern of fields, nuclei, electrons, and probabilities. The nucleus of an atom holds nearly all its mass, while the surrounding electron structure occupies a far larger region. Even matter, when examined closely, is organized around distance. This comparison must be handled carefully. Atoms are not tiny solar systems with electrons orbiting like planets. Quantum physics gives a stranger picture, where particles have wave-like behavior and positions described by probabilities. Still, the scale difference remains striking. The nucleus is extremely small compared with the atom as a whole. What we call solidity arises from interactions, not from every point of space being packed with substance. In that sense, emptiness is not limited to astronomy. It is built into physical reality at multiple scales. A table is mostly structured space held together by forces. A planet is a vast sphere of atoms whose nuclei occupy a tiny fraction of atomic volume. A star is dense compared with interstellar gas, yet even its plasma is a dynamic sea of particles separated by distances at microscopic scales. The universe repeats a principle. Form emerges from relations as much as from filling. This helps explain why the cosmic vacuum feels less alien than it first appears. Matter itself is a disciplined arrangement of emptiness and interaction. Space between galaxies is only the most dramatic expression of a deeper pattern. The physical world is made from fields, forces, particles, and intervals. Remove the intervals, and there would be no chemistry, no structure, No light moving between objects, no room for motion, no distinction between one thing and another. The emptiness inside matter and the emptiness between stars are not identical in physics, yet they rhyme in meaning. Both reveal that existence is not a compact block. It is a set of separations held in order. The atom requires quantum structure. The planetary system requires orbital distance. The galaxy requires gravitational spacing. The cosmic web requires voids. Reality depends on gaps at every scale. This thought changes the emotional quality of the void. Emptiness is often imagined as failure, as if a richer universe would be more crowded. Physics suggests otherwise. Too much density destroys structure. Too little density prevents it. The universe we inhabit lies between these extremes, sparse enough for light and motion, dense enough for stars and chemistry. The emptiness of space is part of that balance. Emptiness is also produced by violence. Stars are born from clouds, but once they ignite, they begin reshaping the environments that made them. Massive stars flood their surroundings with ultraviolet radiation. Stellar winds carve bubbles through gas. Explosions from dying stars drive shockwaves into the interstellar medium. A single supernova can heat, compress, scatter, and enrich nearby material, leaving cavities and shells that may later influence new star formation. Galaxies are full of such feedback. New stars form from gas, then the most massive among them rapidly return energy to the gas around them. This limits how much material can turn into stars at once. Without feedback, galaxies might convert gas into stars too quickly, producing a universe very different from the one observed. Stellar violence regulates creation. It prevents matter from collapsing too efficiently and helps maintain the thin, turbulent medium between stars. Black holes contribute in their own way. At the centers of many galaxies, supermassive black holes can release enormous energy when matter falls toward them. Jets and radiation from active galactic nuclei may heat surrounding gas, push it outward, and limit star formation. In galaxy clusters, such feedback can keep hot gas from cooling rapidly into new stars. The emptiness of certain regions is partly maintained by engines of extraordinary power. Even small bodies participate in clearing. Planet formation involves collisions, scattering, accretion, and migration. Large planets can eject smaller bodies from a system or confine them into belts. Radiation pressure and stellar wind push dust away. Comets evaporate, asteroids collide and grind down. Over long durations, dynamic systems clean their neighborhoods, leaving stable arrangements surrounded by thinner debris fields. The universe is therefore empty for two connected reasons. Expansion spreads matter out, and structure formation clears local regions. Gravity gathers material into stars and planets, while radiation, winds, explosions, and orbital dynamics push other material away. Emptiness is the afterimage of both construction and destruction. It is what remains when matter has been sorted by forces that operate over millions or billions of years. This gives the void a history. It was not simply there as a passive background. It has been carved, widened, heated, drained, and preserved by physical processes. Every quiet region may carry the consequence of old radiation, ancient shocks, vanished stars, or long gravitational rearrangements. Space looks still because we encounter it at human speed. At cosmic speed, emptiness is continually made. Distance is the hidden machinery behind almost every cosmic phenomenon. A star can shine across a galaxy because photons are able to travel through spaces thin enough to preserve their path. A planet can hold a steady orbit because no massive body passes close enough to tear that orbit apart every few thousand years. A galaxy can maintain spiral arms, bars, halos, and streams because its stars move through a gravitational system where direct collisions remain extraordinarily rare. The universe appears dramatic in images, yet its deeper order depends on separation measured across scales that the body cannot feel. This distance also shapes time. When two objects are far apart, change cannot be shared instantly between them. Light becomes the messenger and the limit. The sun may seem immediate from Earth, but its light is already more than 8 minutes old when it reaches the ground. The nearest stellar system is seen as it was more than 4 years ago. Andromeda is seen millions of years in the past. The most remote galaxies appear from epochs when the universe was young, their light stretched by expansion into faint infrared traces. Emptiness turns astronomy into archaeology. The same principle governs communication. If a civilization existed around a nearby star and sent a signal toward Earth, even the fastest possible message would need years to arrive. A conversation across the galaxy would unfold over tens of thousands of years. Across intergalactic distances, dialogue would become almost geological. The emptiness of space therefore imposes a moral and practical solitude on intelligence. Any world that becomes aware of the universe must do so from inside a delay, surrounded by messages that are old before they are understood. Distance also decides what can influence what. The moon raises tides because it is close enough for its gravity to matter on Earth's oceans. Jupiter shapes comets and asteroids because it is massive enough to disturb the architecture of the solar system. The Milky Way and Andromeda are close enough to fall toward a future merger. More distant galaxies, carried away by expansion, belong to a weakening community of influence. The cosmos is not only a map of objects, it is a map of relationships, and emptiness controls the strength of those relationships. This is why the universe cannot be understood simply as a collection of things. It is a collection of separations, delays, and permissions. Some regions are close enough to exchange matter, light, and gravity in meaningful ways. Others can only send ancient light. Others are slipping beyond any possible exchange. The emptiness between objects is an active boundary. It governs causality, communication, memory, and fate. From the human point of view, distance can feel like loss. It turns even the nearest stars into almost unreachable places. It makes exploration slow, fragile, and expensive. Yet the same distance gives the universe its depth. Without it, there would be no ancient light, no layered history, no way to see galaxies in youth and maturity across a single sky. The void stretches space, and by doing so, it stretches time into something visible. Modern astronomy has trained us to expect abundance. Space telescopes reveal nurseries of stars glowing in sculpted gas, galaxies colliding in luminous arcs, clusters crowded with golden ellipticals, and fields where thousands of galaxies appear inside a patch of darkness smaller than a grain held at arm's length. These images are real, but they are also acts of translation. They collect faint light over long exposures, combine wavelengths the human eye cannot see, and compress immense volumes into a single frame. They make the invisible legible by sacrificing scale. A nebula may look like a storm cloud, thick enough to hide shapes behind its glowing folds. In physical terms, its gas can be thinner than the best vacuums on Earth. Its color may come from atoms excited by nearby stars, from dust scattering light, or from infrared emission translated into visible palettes. The image gives us a landscape because the mind needs edges, surfaces, and depth. The actual object may be hundreds of light years wide, so diffuse that a human body placed inside it would not see a glowing wall nearby. The eye would likely find darkness, while instruments would find structure. Galaxies create an even stronger illusion. A spiral galaxy seen from above can look like a solid luminous disk with arms sweeping outward in graceful bands. Inside the disk, stars remain separated by enormous distances. Dust lanes may appear dense, yet they are vast, thin regions spread over unimaginable volumes. Star clusters look like jeweled heaps when photographed, but even in dense clusters, the space between stars remains immense compared with the stars themselves. Images show pattern, not occupancy. The problem is not that astronomy images deceive us. They are among the most truthful tools we possess. The problem is that vision naturally converts brightness into fullness. Where light overlaps, we imagine material density. Where color is vivid, we imagine substance. Where a frame is beautiful, we forget the scale that makes it possible. A galaxy cluster image may feel crowded because many galaxies share the same rectangle on a screen. In three-dimensional space, those galaxies may be separated by millions of light years. This false fullness affects how we imagine travel. Science fiction often turns interstellar space into a navigable ocean dotted with nearby destinations, where ships move from world to world as if crossing political borders. Real interstellar travel faces the opposite condition. Long stretches with almost nothing to encounter, repair from, breathe, mine, or use. The emptiness itself becomes the obstacle. It is not a wall, because a wall is generous enough to give you something to touch. It is a distance that offers no support. The beauty of astronomy survives this correction. In many ways, it becomes stronger. A nebula is more astonishing when we understand that such faint material can become visible across thousands of years of light travel. A galaxy is more impressive when we realize that its apparent fullness is produced by stars separated by deserts of vacuum. A deep field becomes more profound when we remember that each tiny mark contains billions of stars, and that between those marks lie gulfs mostly without light. The universe is visually rich because it is physically sparse. Emptiness does not prevent chemistry. It changes the pace of chemistry. In the densest laboratories of Earth, molecules collide constantly, reactions unfold rapidly, and heat is shared through contact. In interstellar space, particles may travel long distances before meeting another particle. Reactions occur in rare encounters, on dust-grained surfaces, under the influence of ultraviolet light, cosmic rays, and cold darkness. The chemistry of space is slow, delicate, and spread through volumes so large that thinness can still produce abundance over time. Molecular clouds are among the most important examples. They are cold, dark, and comparatively dense by interstellar standards, though still extraordinarily empty by terrestrial standards. Within them, hydrogen molecules form, carbon compounds appear, and complex organic molecules can develop under conditions that seem hostile from an earthly perspective. Dust grains act as tiny platforms where atoms meet and bind. Shielded from harsh radiation, these regions become reservoirs for star formation and for the chemical ingredients that later enter planets. This means that the emptiness of space is not sterile. It carries memory in the form of atoms forged in earlier generations of stars. Hydrogen and helium came from the early universe. Carbon, oxygen, silicon, iron, and many heavier elements were produced through stellar interiors, stellar deaths, neutron-star collisions, and explosive events. Those elements were then scattered into space, diluted into clouds, mixed across galactic time, and gathered again into new systems. Every rocky planet is made from matter that once crossed emptiness after being expelled from older stars. The thin interstellar medium is therefore a slow archive of cosmic recycling. A star dies and releases enriched material. Some of that material becomes part of a diffuse cloud. The cloud drifts, cools, mixes, and may eventually collapse. A new star forms, surrounded by a disk. Dust grains become pebbles. Pebbles become planetesimals, and planetesimals become worlds. Between the death of one star and the birth of a planet, emptiness performs the role of a vast mixing chamber. This gives the void a creative dimension. The atoms in a human body did not travel directly from a single ancient star into Earth. They moved through interstellar space, entered clouds, crossed cycles of heating and cooling, and became part of the material from which the solar system formed. The emptiness between stars did not erase their history. It carried it in diluted form until gravity gathered it again. The same thinness allows fragile molecules to survive in protected regions and allows destructive radiation to carve other regions apart. Space chemistry is a balance between exposure and shelter. In open areas, ultraviolet light can break molecules. In dense cloud interiors, darkness permits complexity. In icy grains and cometary bodies, molecules can be preserved for billions of years. The apparent vacancy of space contains the long preparation of worlds. Where matter gathers enough, emptiness briefly loses its dominance. A star is one such island. Its interior reaches pressures and temperatures high enough to fuse nuclei. releasing energy that pushes outward against gravity. A planet is another island, dense enough for geology, atmosphere, and in rare cases, oceans. A moon, an asteroid, a comet, a ring system, a black hole's accretion disk, each is a place where matter has been concentrated against the general thinness of the cosmos. These objects are rare because the conditions required to make them are selective. A forming star needs a cold, dense region of gas able to collapse under its own gravity. If the gas is too warm, pressure resists collapse. If turbulence is too strong, the cloud is stirred apart. If magnetic fields dominate, they can slow or redirect the flow. Even when collapse begins, feedback from newborn stars may halt further growth. Star formation is therefore a negotiation among gravity, temperature, turbulence, chemistry, and radiation. Density wins only in certain pockets. Planet formation narrows the conditions further. Around a young star, the remaining disk must contain dust and gas arranged in ways that permit growth. Tiny grains collide and stick under some conditions, shatter under others, drift inward, settle toward the disk's midplane, and gradually assemble into larger bodies. Gas giants need enough solid cores or rapid disk processes before the gas disappears. Rocky planets need collisions, differentiation, and survival through a period of bombardment. A stable world is the result of many steps that could have ended differently. Life-bearing worlds are rarer again. A planet must remain stable long enough, receive energy in a useful range, hold the right chemistry, avoid sterilizing disruptions, and sustain cycles that keep its surface from freezing permanently or boiling away. None of these requirements remove the importance of emptiness. The space around a planet helps preserve orbital order. The distance from the star controls climate. The absence of frequent nearby stellar encounters protects long-term evolution. Density creates the world, but distance protects its continuity. Black holes represent another extreme of density. They are formed when mass is compressed so deeply that an event horizon appears. Yet even black holes, those symbols of gravitational finality, are surrounded by emptiness. A stellar mass black hole may be only a few kilometers across in horizon scale, while its gravitational influence extends through a region mostly devoid of matter. A supermassive black hole can sit at a galactic center, shaping stars and gas around it while occupying a tiny fraction of the galaxy's volume. The most compact objects in nature are also reminders of how little space matter actually fills. These islands of density give the universe its drama because they are exceptional. We notice stars because they shine. We notice planets because we stand on one. We notice galaxies because they gather enough stars to become visible across the void. The rule remains thinness. The islands matter precisely because they rise out of an almost endless sea of low density, and every one of them carries the history of a local victory against dispersion. Human beings evolved in a narrow layer of density. The atmosphere is thick enough to breathe. The ground is firm enough to walk on. The sun is near enough to warm us and far enough to spare us. The moon is close enough to raise tides. The stars are distant enough to decorate the night without disrupting the planets. Our senses were shaped for forests, rivers, weather, faces, and horizons. They were not shaped for cubic light years of near vacuum. This is why space emptiness produces a kind of mental resistance. We can say that the nearest star is more than 4 light years away, but the number remains cold. We can say that galaxies are separated by millions of light years, but language breaks before experience begins. We can say that cosmic voids span hundreds of millions of light years, yet the mind turns them into diagrams because it has no bodily comparison. Space is empty beyond intuition. The emptiness also changes our place in the universe. Earth is not located in a crowded cosmic marketplace. It is a small inhabited world orbiting one star in a quiet region of one galaxy, surrounded by distances that make every journey difficult and every signal slow. This isolation can feel severe, but it also explains why our world has remained stable long enough for life to become complex. Catastrophe exists in the cosmos, yet most catastrophe is far away. Every astronomy image is therefore a negotiation with emptiness. A telescope gathers faint light for hours, days, or years. building a visible scene from photons that arrived across immense darkness. A nebula photograph may look dense and bright, yet the gas in the image is thinner than any vacuum we can easily create on Earth. A galaxy cluster may look crowded, yet the galaxies within it are separated by distances beyond ordinary imagination. The camera compresses time and brightness into beauty. The same compression happens in storytelling. We speak of stars as neighbors, galaxies as nearby, missions as journeys, and cosmic events as if they happen in a shared theater. These words are useful. They also hide the silence required for any of those things to be distinct. The universe is not a room full of objects. It is an ocean of scale where objects are rare concentrations, and most of reality lies between them. That is why the emptiness of space should not be treated as a blank. It is a condition of our existence. It allows Earth to orbit calmly. It allows light from ancient galaxies to reach us. It allows stars to live long lives in relative solitude. It allows the universe to have memory, structure, and depth. The void is the distance that lets the cosmos become legible. The future of emptiness may be even more extreme than its past. As the universe continues to expand, distant galaxies will become harder to see. Their light will be stretched toward longer wavelengths, their apparent brightness reduced, their signals delayed across growing distances. Bound systems will remain bound, but regions outside them will recede into deeper isolation. Future observers in a galaxy like ours may see a sky with fewer clues to the wider cosmic web. Stars will continue to form as long as galaxies retain cold gas, but that supply is finite. Over enormous timescales, gas will be consumed, heated, expelled, or locked into long-lived stars and remnants. The brightest stars die quickly. Smaller stars endure for vast durations, especially red dwarfs, whose slow burning may outlast the current age of the universe by staggering factors. Yet even stellar light belongs to an era, and eras pass. In the deep future, the universe may become a realm of remnants, white dwarfs cooling in darkness, neutron stars fading, black holes isolated across expanding space, planets frozen around dim relics, and rare interactions unfolding over timescales that dwarf all human history. The emptiness between these objects will grow in significance. The bright age of stars may appear from that future perspective, like a brief luminous interval in a much longer dark chronology. This does not make the present small in value. It makes it precise. We live during a time when the universe is old enough to contain heavy elements, planets, and life, yet young enough to remain rich with stars and visible galaxies. The sky still carries evidence of the beginning. The cosmic web can still be mapped. Distant galaxies still send light that instruments can gather. We inhabit a temporary window in which emptiness has not yet hidden the larger story from view. The question, why is space so empty, therefore points toward time as much as space. The universe is empty because it expanded, because matter was limited, because gravity gathered unevenly, because feedback cleared regions, because dark energy now accelerates separation, and because structure requires room. The answer is not a single mechanism. It is the biography of the cosmos, written as distance. When we look into the night sky, we are not looking at a crowded ceiling. We are looking through the great condition that makes sight possible. The stars shine because the dark between them allows them to be seen. Galaxies reveal their shapes because they are suspended in enormous separation. Earth endures because the universe has given it space enough to move, cool, gather oceans, and hold life under a thin blue atmosphere. The emptiness of space is not the absence of meaning. It is the scale on which meaning became possible. It is the silence that preserves the signal, the distance that protects the world, the darkness through which ancient light continues its journey. The universe is vast because it is mostly void, and because of that void, a small planet can look outward and read the fire of places it will never touch. There is a temptation to imagine a fuller universe as a richer one, with stars closer together, galaxies within easy reach, and no immense darkness between destinations. Yet such a universe would be less stable, less transparent, and far more violent. Worlds would be disturbed by passing stars. Skies would blaze with dangerous radiation. Light from the deep past would be harder to preserve. The delicate distances that frustrate exploration also shelter the conditions that allow observers to exist. Space is empty because the universe is governed by scale, expansion, gravity, and time rather than by human expectation. Matter gathers where it can, shines for as long as it can, and leaves the rest open. The void is not an error in the design. It is the design's largest feature. It holds the planets apart from the sun, the stars apart from one another, the galaxies apart across the cosmic web, and the ages of the universe apart in the light that travels between them. To ask why space is so empty is to discover that emptiness has never been simple. It is ancient expansion made visible. It is gravity's unfinished work. It is the aftermath of star formation and the condition for future stars. It is the transparency that gives astronomy its reach, and the isolation that gives worlds their safety. The universe is not a crowded chamber. It is a vast, structured quiet, crossed by rare fires. And somewhere inside that quiet, on a small planet circling an ordinary star, matter has become aware of the distance around it. We measure the void, fear it, use it, and fill it with names. We send instruments into it, photons through it, questions across it. The emptiness remains larger than every answer, yet every answer needs it. Space is so empty because only an empty universe could become this deep.